Hello, everyone. Today, I'm going to talk about our project about building a scalable distributed massive MIMO baseband processing system. This project was done with Anuj from Microsoft and my advisor Minlan. Today, we are going to move to the 5G era. The mobile traffic rate demand is increasing by a lot in the last few years. So here is a figure of total 5G traffic rate. It shows that the traffic rate increased in the past few years and predicts the rate increase in the next few years. To satisfy the increase in traffic rate from 5G, one of the key new features of 5G for higher throughput is called massive MIMO. So massive MIMO is a technique of using a lot of antennas at the cell tower to simultaneously serve many users at the same time, at the same frequency. So it can support higher throughput. So here is a cell tower, and the key component inside here is the radio unit, which consists of an array of antennas. Let's say we have M antennas and K users, and here we call it M times K massive MIMO. The larger number of antennas are used to implement a technique called beamforming, which focuses the radio directly to the users. Because of beamforming, there is little interference among the users, even they are sending and receiving the data at the same frequency. Therefore, the massive MIMO technique can achieve higher throughput. However, making massive MIMO scalable to more users and more antennas is challenging because of the high computation and wide communication costs from massive MIMO. The RU sends the signals from the users to a component called the baseband unit over Ethernet link, which converts these front-haul packets into user bits. And the traffic to carry those radio signals is called front-haul traffic. Historically, the BBU has been implemented in specialized hardware like FPGA or DSP. However, these days there is a movement to virtualize the RAM by running the BBU on commodity servers. Like virtualizing network functions, it can mitigate when the lock-in has flexible development and high velocity development. According to the news, many companies have already built and deployed their own 5G BBU software solution. This is great, but it presents a problem because of the very high amount of computation and high front-haul bandwidth required by massive MIMO. There are some recent work on designing efficient massive MIMO processing systems on commodity servers, like the Agora. The problem of Agora is that it is limited to one single server, so it cannot scale to the increasing number of antennas and users. Agora requires 28 cores for supporting 64 antennas and 16 users. If we want to go to a higher configuration, like 128 antennas or 32 users, we need to design a distributed system where we can use the computation resource across multiple servers. To understand how our system improved the scalability of massive MIMO, let's take a look at the scalability bottlenecks in existing state-of-the-art designs in both the distributed and single-server settings. Existing state-of-the-art systems suffer from high communication overhead, which limits their scalability. For example, the state-of-the-art distributed solution is called Big Station. Its scalability is limited by the high inter-server communication overhead. The single-server system Agora also suffers from inter-core communication overhead in its design, and that also limits scalability. Now, let's talk about our solution, Hydra, a scalable distributed massive MIMO system. In Hydra, we optimize both inter- and intra-server communication overhead. In this talk, I will focus on the distributed aspects of the system that optimizes the inter-server communication overhead. For single-server improvement, Please refer to our paper for more details. To reduce the inter-server communication overhead, Hydra first exploits the features of modern RUs to deliver the front-haul data directly to servers, instead of shuffling data among servers in prior designs. Second, we observed that the massive MIMO processing pipeline progressively reduced the amount of data, like converting the floating point wireless signals into user bits. Therefore, to minimize the amount of data exchanges, Hydra delays the data shuffling until later in this pipeline. Before talking about our ideas, let's look at the massive MIMO processing pipeline. Prior work has shown that the massive MIMO processing pipeline has different types of parallelism at different stages: the antenna parallel stage, subcarrier parallel stage, and the user parallel stage. The antenna parallel stage means that antennas can be processed independently and in parallel. This is similar in the later two stages. For uplink processing, when the BBU receives the radio signals, the signals are first processed by FFT at the antenna parallel stage, and then processed by equalization and demodulation in the subcarrier parallel stage, and finally processed by forward arrow correction in the user parallel stage. The downlink processing is similar. To understand how Hydra optimizes inter-server communication overhead, let's look at how the design of the big station suffers from inter-server data communication overhead. The first overhead comes from the data dependency between adjacent stages of the pipeline. Let's take a hypothetical example where we have 120 antennas and 30 users with 1,200 subcarriers, and we are running on 3 servers. Let's first partition the workload for the antenna parallel stage. Since in this stage, the data is antenna parallel, we can simply partition the 120 antennas into equal ranges, 40 antennas per server. So here we have the first server process antenna 1 to 40, the second one 41 to 80, and third one 81 to 120. We can do the same thing for later stages as well. So now let's focus on one packet at each server. After the antenna parallel stage processes each packet, the packets are ready to fed to the next stage. The challenging thing here is that the data rate to be fed is very large, around 128 gigabps. Note that all the packets hold the data for all 1,200 subcarriers in the system, while each server in the subcarrier parallel stage processes different non-overlapping set of subcarriers. Therefore, it is not possible to simply forward the packets directly to the next stage on the same server. To feed the data correctly, each server needs to partition the packet into 3 subcarrier sets, and then forward each partition of the subcarrier data to the corresponding server. This requires shuffling all the data that we receive from the radio between the servers, causing more than 120 gigabps of inter-server shuffling. To address this overhead, Hydra exploits the feature of modern RUs to eliminate such data shuffling. In almost all modern virtualized RAM deployments, the RU should support FFT, so we can offload the antenna parallel stage from the servers to the RU. Now the packet is processed in the RU. However, to feed the packet to the next stage, we still need to forward this packet to all servers by duplication, because the packet still consists of data for all subcarriers. Therefore, simply offloading FFT to the RU does not eliminate the data shuffling. The good news is that the modern RUs support another feature, which is configurable front-haul packet segmentation. This feature is originally for MTU size tuning, which allows the large front-haul packet to be segmented into small sizes so that they can go through the network with smaller MTU sizes. Here we can use it in a new way for scalable front-haul packet delivery. We can configure the RU to partition the packets based on the different subcarrier sets processed by different servers, and then forward each partition to each server correspondingly. With this idea, we only need to forward the data once to all the servers without any extra inter-server data shuffling. Let's switch to our second idea for reducing inter-server communication. Hydra's second idea comes from our observation that the massive MIMO signal processing pipeline progressively reduces the data size. So if we can delay the inter-server data shuffling as much as possible, we can make the system more scalable. Let's go back to our hypothetical example with 120 antennas and 30 users. After FFT, we have data for all 120 antennas fed to the equalization stage. The rate is around 128 gigabps. Then the equalization stage transforms the data from the antenna domain to user domain, converting the data from 120 antennas to only 30 users, causing a 4 times data reduction. This reduction is general because the number of users in massive MIMO is usually much smaller than the number of antennas. The demodulation stage converts the 8-byte floating point wireless signals into intermediate representation of user bits, which is around 6 bytes, resulting in another 25% reduction. Therefore, if we can delay the data shuffling until the user parallel stage, it is more scalable. Our system, Hydra, decides to delay the shuffling at this point. This decision from Hydra is very important because inside the massive MIMO pipeline, there are a lot of sources of parallelism. So it is intuitive to exploit all the parallelism as much as possible. But that limits scalability because it introduces high communication overhead. Now I will give you an example of how the state-of-the-art solution Big Station exploits the parallelism without optimizing the communication overhead. Let's look at the matrix inversion task for subcarrier 800, which is required by massive MIMO here. And there are lots of large matrix inversion tasks in Big Station. Big Station aggressively partitions the task around multiple servers to reduce the processing latency. This makes sense when the CPUs are weak, because otherwise the latency for this task is too long. However, when we have more antennas and users, we have higher communication overhead across servers. In contrast, Hydra decides to affinitize all those tasks in a single subcarrier to a dedicated server, and delays the shuffling until the user parallel stage. This minimizes the inter-server communication overhead. Let me introduce our evaluation setup. We have 4 commodity servers, and each server has 2 16-core CPUs with AVX2 support. And each server also has 100 GBE NIC. We use 3 servers for Hydra and 1 server to run RU emulator. Our experiments show that Hydra is more scalable than existing systems. Let's look at the end-to-end performance comparison between Hydra and the existing Big Station and Agora systems. Here, the x-axis shows different massive MIMO settings, and the y-axis shows the minimum number of CPU cores required for different cases. Our results show that Agora requires 28 CPU cores for 64 × 16 MIMO, and cannot support higher MIMO dimensions since it is a single server solution. Big Station requires 44 cores for 64 × 16 MIMO, which already spans 2 servers, while Hydra requires only 19 cores. Compared to Big Station, we see similar results for 128 × 16 MIMO. For even higher MIMO dimensions, like 128 × 32 and 150 × 32, Big Station cannot support them with 3 servers. while Hydra can support them with 53 cores and 70 cores respectively. To evaluate Hydra's performance on more servers than our 3 server nodes, we also ran experiments on a larger cluster with 27 10-core servers in Cloud Lab. We found out that Hydra can support 256 times 32 MIMO in this setting with 18 servers. So here is a conclusion. In this presentation, we show that the inter- and intra-server communication is a key scalability limiter in prior massive MIMO designs. And Hydra's high scalability comes from using the features of modern RUs in novel ways, and it's also efficiently partition the computation across different servers to reduce the inter-server communication overhead. So Hydra supports 150 times 32 MIMO for the first time in software. And we believe that Hydra's high scalability makes rapid development and deployment of 5G networks possible. So thank you so much. I'm happy to take any questions.